Hey guys, what's up? DTHT back with another video. Today we're going to be talking about 2's complement. Now before I get into the 2's complement, I want to quickly review how to convert from binary to decimal and decimal back to binary. Right, let's start with the binary number 0, 1, 0, 1. And well, we'll convert later the number 6 into binary. So for 0, 1, 0, 1, what we're going to do is write out the places for binary. Now we know that this is going to be going by the power of 2's, right? So the first place is going to start with 1, the second is going to be 2, the third is going to be 4, then 8, and then 16, then 32, and on and on. Right, so given this fact, we can figure out that, well, 0, 1, 0, 1 means that we're going to have 1, 1, right, plus 1, 4. And 4 plus 1 will give us 5. So the decimal value, right, the decimal value of 0, 1, 0, 1 is going to result in 5. Now, what about the number 6? Right, what's going to happen with 6? Well, this is going to be something a little bit more difficult because we're trying to figure out what combination of one of these numbers will result in the number 6. Well, in this case, it's quite simple because 4 plus 2 is going to give us 6. So we can just write 0, 1, 4, 1, 2, and 0, 1s, right? This is the 8's place, the 4's, the 2's, and then the 1s. So this 4 plus 2, right here, because we have 1, 4, and 1, 2, this is going to result in 6. So the binary of 6 is going to be 0, 1, 1, 0. So using that way of converting decimals into binary, people started computing out the binaries for a whole bunch of numbers. Now in this example, we're going to be only dealing with 4 bits, so meaning that we have this 1, 2, 3, and 4 bits. So we're not going to be worrying about numbers that are bigger than 7, right? Because using these 4 bits, we can only form the maximum number of 7. Now this is for a reason, right? You might be thinking, why can't we use that last bit? Well, people thought while they were designing this, how are we going to represent negative numbers using binary units? Right? We have positive numbers written out here, but what are we going to do with negative numbers? So someone brilliant came up with the idea of using, right, let's say for instance the number 0011, which is equal to 3, right? He thought, why don't we use this bit and call this the sign bit? So what this means is that this bit is going to denote whether it is a positive number or a negative number. So a 0 is going to mean it is a positive number, and a 1 will mean that it is a negative number, right? So to make 3 into negative 3, all we want to do is change that first 0 into 1 and then just leave the rest the same. So this is what they thought will work out. So then they wrote this out. So here I have this written out in the way that we just converted, and we have it from negative 7 to negative 1, just as we have the positive numbers 1 through 7. Right, so this presents 2 problems though. The first problem is that because we're working with 4 bits, it means that we can have 16 different combinations of these 1s and 0s, meaning that we should be, in theory, be able to hold 16 different numbers. Now if you take the time and count up how many numbers these are, it will come out to 15 different numbers. So where is that 16th number going to go? Well, scientists didn't really know what to do at that time, and they just made a negative 0 as 1, 0, 0, 0, and well, they just set it to negative 0. And this is where the second problem actually comes in, because if we do some sort of arithmetic with this, right? If we do, like, let's say 3 plus negative 2, 3 plus negative 2, well, in decimal systems we will get the answer of 1, but let's try that with binary, right? That 3 is going to be 0, 0, 1, 1, plus, right, we're going to have negative 2, which is 1, 0, 1, 0. Now if we do the math right here, it's going to come out to 1. 1 plus 1, obviously that's 0, we carry that over, 1 comes down, and another 1 comes down here. Now this result is going to be negative 5, not 1, right? This is completely wrong. And you could try this with any one of these numbers, and it's always going to be just some random number out of these 16 digits. So this is one big problem that existed. Now to try to solve this problem, there's this new thing called 1's complement that was created. ones complement said that for every one of these negative numbers, what we're going to do is we're going to get the inverse of the positive binary to represent these negative numbers. So what I mean by this? Well, you could take the number, let's say 3 again, that's going to be 0, 0, 1, 1, right? That equals 3. And what we're going to do is we're going to flip the zeros to ones and the ones to zeros. So this will be in negative is going to be 1, 1, 0, 0. And that is going to represent negative 3. So, well, they wrote this out again. Now here I have, once again, written out the negative numbers, but now in obviously ones complement, right? And the negative 0 is still going to exist. Now this time it is obviously going to be the opposite of this. So this is still going to be 1, 1, 1, 1. And that's going to be equal to negative 0. So the negative 0 still does exist, but we have actually gotten quite a bit closer than we were before. Now let's try out that same math as we did before. 3 plus minus 2, right? This still is going to be 1. Now if we try that out with binary, this is going to come out to 0, 0, 1, 1 plus negative 2 is going to be 1, 1, 0, 1. Now if we do the math out, it's going to come out to 1 plus 1, 0, carry that over, 1 plus 1, 0, carry that over, 1 plus 1, 0, carry that over, 1 plus 1, again 0, and that number carries over. Now since we're only dealing with these 4 bits, this last one does not really count, and what we're left with is this 0, 0, 0, 0, which actually equals to 0. So it is going to be 1 less than what we actually need. Now you can try this out with any of these other numbers, and it's always going to be 1 less than what we actually need. So why don't we just try to shift these negative numbers 1 down so that we will be at the right number. And this is where 2's complement is going to come in. We're going to leave the positive numbers alone, but in 2's complement what we're going to do is for every single one of these negative numbers that is written out in using one's complement, we're going to add 1 to that, right? So if we want to change these values, let's say for instance negative 2, which is 1, 1, 0, 1, is equal to negative 2 by 1's complement. If we want to make it into 2's complement, we'll just add 1 in that binary term. So that's going to be 1 plus 1, 0, carry that over, 1, 1, 1. So this new number is going to be the true representation of negative 2 under 2's complement. Now that we have 2's complement finally written out over here for these negative numbers, negative 1 through negative 7, we can notice a few things. First of all, we don't have that imaginary 0 over here anymore. We're just going from 0 to negative 1 immediately. So shifting everything down 1 actually solved that problem of having that negative 0. That is now completely gone. But that opens up the fact about that 16 digits we have, right? 16 different numbers that we can hold. So what is going to happen to that 16th number? Well, scientists way back in the day just thought that we should have that 16th number as a negative 8 right over here at the top. So in 2's complement, we're always going to have one more negative number than the highest possible positive number in the number of bits that we have. Now that we've solved the problem of the 16 different numbers and also that negative 0, why don't we try the final test, right? The test of addition. So let's do the same numbers, 3 plus minus 2. Now this again is still going to be 1, as we always know. And why don't we try that with the binary system? This is going to be 0, 0, 1, 1 plus negative 2, which is 1, 1, 1, 0. So why don't we try this out? So 1 plus 0 is going to be 1, 1 plus 1, 0, you carry that over. This again is 0, you carry that over, again 0, and then obviously we have this extra bit, which we don't count because we're still dealing with only 4 of these bits. Now 0011, as we already know now, is going to equal positive 1. So we've finally gotten the right answer after we came to 2's complement. So here we are at the end of the 2's complement video. I hope you guys enjoyed it. Just a quick review before we end. To convert a positive binary value to a negative binary value, we'd want to first go to 1's complement by flipping the zeros to 1's and the 1's to 0's, and then we would want to add 1 to that 1's complement number to finally get the true value of that negative number in binary. So I hope you guys enjoyed this video. If you guys did, feel free to give this video a thumbs up, If you guys didn't and you have more questions, put those in the comment section below. And if you want more of these videos, feel free to hit that subscribe button because those are going to be churning out very, very soon. I'll catch you guys in the next one. See ya.